All right, now we're going to get into the heart and soul of electronics. So the first thing we're going to talk about is the physics of electricity. How does this work? Because that is what I am after specifically, is how do the electronics work, and that's what we want you to know. So the first thing that we're going to do is we're going to go back and get really, really small. So what we're going to look at is the smallest unit that we have of matter, the atom. What is it? The atom, again, like I said, it's the basic building block. It is what defines what a thing is, what it's made of, is based down on this atomic scale. So it's the smallest unit that retains the properties of an element. And it is built upon a series of parts. We have protons, which are positively charged. So our positively charged is protons. We are also made up of neutral portions. Oops, make this eraser a little smaller. Do that one right there. So we'll redraw this. So we've got neutrons, another proton, and another neutron, another proton, another neutron. So what we have here, this is our neutrons. Protons have a positive charge, neutrons are neutral and don't have any charge. And then buzzing around what we call the nucleus, where the protons and neutrons live, we have these parts of the element that we called electrons. And the electrons are negatively charged. So depending on what type of material this is, it's going to have different numbers of protons and neutrons. Those two are going to make up the bulk of the atomic mass of the element. And then the neutrons are going to be based on where the element sits in the periodic table. So if we kind of look at an idea of the periodic table, we're going to have it look like this. Okay, so we got one side and we have the other side. To the left over here, this is where we have one electron in its outermost shell. In here, we have 8 electrons. So what happens is our electrons are going to fill up the shells of the element that they have. Depending on how many electrons, that's how many shells they have. In the outermost shell, we have 8 electrons. So this column over here, this is what we call our noble gases. This row of elements, this column of elements, they have 8 electrons in their outer shell, meaning they don't want any electrons and they don't want to get rid of any electrons. So these guys are stable. This is helium. This is, I can't remember the elements all of a sudden. Neon, things like that. So xenon, those are the ones that we use on that side. The ones on the far right-hand side, they have 1 electron, meaning they want to get rid of it or gather some more to make up their total, but most of the time they're going to get rid of it and get rid of that 1 electron that's sitting there. In the center section, this is the elements that we work with most. This has got 3 to 5, maybe 6 electrons sitting in there. These are our metals. They are willing to accept an electron or they're willing to get rid of an electron. And sitting in the middle of this cluster is one of the elements that we use quite often in electronics, which is copper. And we use copper because it can either take electrons or give away electrons really, really well. And it's sitting with 4 electrons. So it's willing to do whatever it needs to do to fulfill its outermost shell so it's full. So what we do with this idea is with the different elements that we have, we are after the electrons. We want the movement of electrons. That's what electricity is. Electricity is the movement of electrons or flow of electrons through a material that does work for us. So that does work. Okay, so we're using those electrons to emit light, create heat, move signals around, transfer information to one point or another, but the physics of it is these electrons are moving away to a different element, those are traveling along the lines, or we're getting new electrons that come into this element. And copper is one of our better ones that we use, just for the amount of electrons that it has available and that it can store, and it moves either direction with what it needs to do. So when we kind of look at this, when we look normally at our electrons and what they're doing, so the first thing we're going to do is imagine that we have a piece of copper wire sitting here, and we have a bunch of our electrons just kind of hanging out inside this piece of copper. Now this electron might be coming over here, this one might be moving this direction, this might be coming over here, this one might be doing loop-de-loops. Whatever it may be, all these electrons that are in this piece of metal are not doing anything. They're just kind of bouncing around and applying nothing. They're just existing. That's it. So what happens is because of that, that doesn't give us a very good effective medium to do any sort of work with because they're just randomly moving. This one may run up and bounce against this wall, and then it'll come down here. We may have some of them collide. So what we want to do is we want to take these electrons. Now we know, like I said earlier, is the electrons are negatively charged. So with these electrons that are hanging out inside this copper piece of wire, or whatever metal that we're using, if we apply a charge to these electrons or to this wire, or we apply a voltage to it, or a magnetic field even, we want to be able to get these things to move around. So if I apply a positive force on this side, so we have a positive entity over here, we have a negative polarity over here, these electrons are going to see this negative polarity and they're going to shift. They're going to move away from that negative and be attracted to that positive. So now all of a sudden, once we apply a force, a voltage, or a magnetic field, or whatever it may be, where we induce a positive polarity and a negative polarity, these electrons are now going to move all in the same direction. That movement of those electrons is electricity. That's how we get it to move them. So now those electrons are just going to be traveling all the same direction, and suddenly we get a big mass of electrons moving through a copper wire. Now, some of the things that we need to talk about with this concept. So we have, first of all, is how they move, what they're called. So we have electrical charge. So electrical charge simply is defined as the number of electrons present in an area. And I'm going to call it a volume. So in a piece of wire, it's the number of electrons that are present. Charge is designated as a Q, as the thing, and we measure it in coulombs, which we designate that with a capital C. So if I'm looking at the charge of a piece of wire, it could have 150 millicoulombs of charge inside that object of whatever it is. Like we learned about in our scientific units, SI units, that Q is the thing, C is the unit, so therefore the C is going to fall under coulombs, versus if it was the thing, we'd be talking about capacitance if the C was over here. So remember to keep those things straight and not mix them up. The way that we get this value Q, so the charge is equal to the number of electrons present divided by 3.25 times 10 to the 18th power, and again that's measured in coulombs. So it is quite literally the physical amount of electrons present in a volume divided by that number, 3.25 times 10 to the 18th, that gives us the charge or the potential of this device. So the physical charge of however many electrons are present. We can change that, we can increase that, we can decrease it by adding to or taking away the electrons. All right, so now that we have our electrical charge, we can look at the next idea, which is voltage. Voltage is designated by the symbol V, capital V, and it's measured in volts, which is also capital V. So voltage we get easy on the SI units. V is the thing, and V is what it's measured in. So voltage is defined as the amount of energy needed to move a charge measured in volts. So the amount of energy that's needed to move this electrical charge, which is the number of atoms, the number of ions, electrons, sitting in a location. So how much energy is needed to push those guys around? The way that we get this formula is voltage is expressed as the work or energy measured in joules divided by the charge, which is Q, measured in coulombs. And that gives us voltage. So the amount of energy needed to push around the number of electrons that are sitting there. Makes it really easy. And what we get here is voltage is also the potential energy between 2 points. So how much energy would it take to move the electrons from one point to another that we're measuring? All right, so we got voltage. So charge again is the physical number of electrons. Voltage is the amount of energy or the force that is needed to push around said number of electrons. And then the next thing we're going to talk about is current. So current is designated as this. So current is designated as a capital I, and it's measured in amps, which is a capital A. So current, when we break it down, is the physical movement of the electrons. Or the number of electrons moving past a point per second. Current, in mathematical terms, I is equal to the charge divided by little t, which is time. So when we come back and look, again, reviewing this all, the electrical charge is just the sheer number of electrons present in an area, or in a volume, I guess I should say, not an area because we're dealing with 3 dimensions, not 2. So electrical charge, the amount of electrons in the volume. Voltage is the force that is required to push those electrons around and move them in one direction. And then the current is the physical movement of the electrons past a specific point per second. So that's how all those tie together. And then after we have current, we have another concept that we're going to learn about. This one is called resistance. Resistance is designated with a capital R, and it's measured in ohms, which is the Greek capital omega. And what resistance is the opposition to current. So resistance, the whole idea is to put things in the path of current to slow it down. So it makes so electrons, they have to go around obstacles and change the path of the electrons. Which effectively lowers down the amount of electrons that are passing past a certain point per second. So it restricts the flow of it. It makes it so not as much current can flow. And the biggest thing that we do with resistance is if we look at our copper wire, what it is going to be, it's going to be impurities. So this could be a little piece of carbon. Okay, we could also have a little piece up here of tin, or something that was in the process when this copper wire was being made. We could have iron. Whatever it may be, just in the process, we're going to get these manufacturing defects that have a natural resistance to electrons flowing through. So then what happens is as this electron is come buzzing through here, it hits that impurity and it can't pass through it because there's either something there or there's not a spot for the electron to go into a shell. So it has to go around, which then in turn slows down the total number of electrons that can be seen passing past this point. So if we look and we have an eye sitting right here, looking out. As these are moving, because these little divots or these little imperfections come in, we see a smaller number of electrons moving past. So we're going to get a smaller current. All four of these work hand in hand. The amount of charge is directly related to the current. The number of electrons present is going to be determinant of how many electrons are able to be pushed around. Now we can change this charge based on the material. We can change this charge by introducing electrons from another source into the area we're at, things like that. They can also absorb electrons that are free floating in the air. They can, do a lot of things. They can take photons, which is light, and as those lose energy, they emit electrons, which then can be measured and changed. So they all tie into each other on the basic physics of these electrons that are floating around these atoms connected together in different metals and elements and things like that. So again, electrical charge, the physical number of electrons that are in a volume. Voltage is the amount of energy or work or force that is needed to move the number of electrons sitting there. The current is the physical movement of those electrons, how many of these electrons are passing a point per second. And resistance is the opposition or slowing down of the current. Easiest way to think of that is this is what we're putting in front of the path of those electrons, so they have to change course and slow down to get those different outcomes of what we want.